All right, let's talk about data. We're going to see how we can take a huge, messy pile of numbers and, with just a little bit of Python, turn it into a story that actually makes sense. We're going to find the hidden insights hiding in plain sight.
Because, when you first open a data set, it can feel like you're just staring at a wall of numbers, right? It's just a sea of digits without any real meaning. So the big question, the one we're going to tackle right now, is how do you break through that wall? How do you find the narrative that those numbers are dying to tell you?
Well, the trick is to look at your data through two different lenses. And I want you to think about it like this. First, you've got Descriptive Statistics. That's your map. It shows you the terrain of the data you have right in front of you, the shape of it, the main landmarks. Then, you've got Inferential Statistics. That's your compass. The compass helps you use that map to navigate, to make really smart guesses about the bigger world your data represents. Map and compass. That's our game plan.
So let's kick things off with part 1, mapping your data. Before we can even think about making predictions, we have to get a really good handle on what we're actually looking at.
So, what are descriptive statistics? Honestly, they're just the tools we use to summarize and organize everything. This is how we find the center of our data, the average, how spread out it is, and just its overall shape. We are literally drawing a map of our dataset.
And here is the absolutely beautiful part. If you're using the Pandas library in Python, getting this entire map is as easy as typing one single command, df.describe. That is it. Seriously, you just point it at your data, and boom, you get an instant summary of all the key features.
And check this out. Here's what it looks like in action. We're using a data set about professor salaries. Instantly, describe tells us the average, the mean, salary is about $113,000. But look at the standard deviation, 30 grand. That tells us there's a huge spread in what professors make. And the quartiles, they show us the distribution perfectly. A quarter of them earn less than 91K, while the top quarter make over 134K. Just like that, we've mapped out the entire salary landscape.
And when we actually put that data into a chart, the story becomes crystal clear. When you group by academic rank, you see this undeniable step-by-step jump in salary from assistant to full professor. And this isn't just some academic exercise. This exact kind of analysis is what HR departments do every single day to figure out fair pay.
Okay, time for part 2, navigating beyond the map. We've described our data. Now, let's actually use it to make some predictions. It's time to pull out the compass.
And now we can start asking those juicier questions, right? Like, we have a hunch that more experience probably leads to a higher salary. But can our data actually prove that? Can we put a number on that relationship? This is exactly what inferential statistics is for.
So yeah, inferential statistics is our compass. It's the whole set of techniques we use to take our sample, in this case data from 397 professors, and make an educated guess, or what we call an inference, about all professors everywhere. We're using the little bit we know to predict the whole lot we don't.
A fantastic tool for this in Python is the Statsmodels library. And I love this part. The way you ask your question is so intuitive. This little formula, salary tilde PhD, is literally just you asking the computer, hey, can we explain salary based on the number of years since someone got their PhD? That little squiggle, the tilde, is just a stand-in for, is there a relationship here?
Now, when you run that model, you get a ton of info back. But there's one number you should look for first, the R-squared. Just think of it as a score for how good your explanation is. An R-squared of 0.45 here means that the factors we looked at, like experience and rank, can explain about 45% of the reason why some professors make more than others. That's actually a pretty strong explanation.
So what did we actually find? Well, our model totally confirms it. Experience and rank are really significant predictors of salary. But the bigger picture here is that this isn't just about professors. This exact same technique, it's called regression analysis, is used to study incredibly important things like pay equity, to see if unfair salary gaps exist even after you account for things like experience.
So having these powerful tools is one thing, but knowing which one to use, and maybe more importantly, what common mistakes to avoid, that's a whole other level. Let's talk about the tools and the traps.
In the Python world, you've basically got two main toolkits for this stuff. There's Statsmodels, which we just used. It's fantastic for explaining relationships, for understanding the why. Then there's Scikit-learn, which is the absolute king of pure prediction. It's less concerned with why and more focused on getting the most accurate forecast, even if the method is a bit of a black box. So, Explaining versus predicting. You got to pick the right tool for the job.
And you have to be so careful about the common traps, things like p-hacking, which is basically just fishing around in your data until you find a result that looks interesting. Or this thing called multicollinearity, where two of your clues, like years with a PhD and years of service, are so similar that they just end up confusing your model. These are the kinds of subtle mistakes that can lead you to completely wrong conclusions.
And that brings us to what might be the single most important rule in all of statistics. Just because two things move together, like ice cream sales and shark attacks both go up in the summer, it doesn't mean one is causing the other. There's almost always a hidden factor, like the hot weather, that's driving both. You can never, ever forget this rule.
Okay, let's bring it all home. I want to give you your final takeaway. A simple, repeatable process you can use every single time you're faced with a new pile of data.
It all comes back to our big idea. Step 1, describe. Use your tools to draw the map of your data. Really get to know its terrain. Then, step 2, infer. Pull out that compass. Use the map you just made to navigate, to test your ideas, and to make predictions about the world outside your dataset. Map, then navigate. It's a powerful workflow that will never, ever steer you wrong.
So there you have it. You now have the tools to go way beyond just a wall of numbers. You have a map to describe the what, and you've got a compass to start predicting the why. So the only question left is, what story are you going to uncover next?